I'm thinking about it. Yeah. Yeah, okay. So there's the submit test work. It's due. The last day this will accept is the day after the test due. So the test is due Monday, 26th. You need to submit the work within 24 hours. This link was not available when the test opened. So this one I'm not going to be as much of a stickler about it being in 24 hours since some of you took the test already. But if you haven't taken the test, please make sure you get that work in as quickly as possible. What I don't want is other work coming in or anything like that. Yeah, you're gonna submit that week. If you've already submitted it, it's no problem because a couple of people have already submitted their work. They completed the test and submitted the work. But if you haven't done that yet, please do, because remember, we're dealing with the situation where we don't have a lockdown browser. So getting the right answer is not the most difficult part of a math problem. If you have access to the internet, showing you understand the math problem is the most difficult part. So that's what I'm testing for. I also just sent out a message for those of you that have a Chromebook. So if it's your Chromebook and you feel comfortable, you'll test that process put up by. If you'll check, let's see. That announcement is right here. This is from the Alamo College District, and they've got the instructions here for students. So we're asking you to install the lockdown browser if you have a Chromebook, add to Chrome, add extension, restart your computer, and then bring it up. And what I've posted, the only thing you need to know is whenever it says Canvas, just think Blackboard. Now it says quiz, so I'm probably going to post a couple more assignments just to see if we can make the lockdown browser work for us at all. But right now, what you have are two assignments, two practice tests. They don't count toward a grade, don't worry about that. But if you look in your assignments folder, you'll see practice tests, lockdown browser, how's it worded? Practice test with Respondus no webcam, practice test with Respondus with webcam. So one uses the webcam, one doesn't. If the webcam feature is not available, I just need to know that. And then I'm going to create a practice quiz with the Respondus because the whole thing's just a little funky. So if it'll let me use the lockdown browser even partially on a quiz, then I'll just title your tests as quizzes. We can have the lockdown browser at work, and then showing your work while it's still important isn't going to be the end all be all. All right. So any questions from test review from chapter R? Anything out there? Everybody's good? All right. Well, in that case, let's move on. So the test, so the last test is going to come in on the 26th. The last work will come in on the 27th. And then, so I'll start reviewing the tests on the 28th. Yeah, I'll start reviewing on the 28th, and that'll take me forward. It'll take me 2 or 3 days to get through everything, especially since I'm focusing so much on the work. All right, so there it is. The only thing you have due over the weekend is the 1-3 homework. I'm confident we can get through 1-3 today without a whole lot of trouble. So we're gonna go ahead and work off that assumption. It's due next Tuesday, so that means you will see me again before it's due. But I do want you to go ahead and, like I said, we're trying to move forward So let's just keep doing that. All right, so 1.3 is all about functions and relations. And you see our 5 objectives here at the top. Now, relation is not a word that we see a lot in math because we know about functions. Functions are special types of relations. Right? They're a unique type of relations. A relation is just a relationship between two values. That's all it means as a relation. So when I have two sets of values and I want to talk about the relationship between the two of them, what I'll bring up is an ordered pair, x comma y. All right. So the set of ordered pairs, x comma y, is called a relation in x and y. What are some examples of things that could be related? Well, we had the car that needed to stop in order to not hit the deer. There's a relationship between how fast you're going and how far it takes you, how far down the road it's going to be before you can stop. The book does a good job of giving you a bunch of examples. Since it's not locked down, it's unfair. Andrew asked if the Desmos is allowed. If I say it's not allowed, I can't stop it. So the only people I'm punishing are the people that are honest. So there's no point in me blocking it. There's no point in me saying don't use it when if you do use it, there's no possible way on that. So no, it's available. Yeah, that's absolutely fine. All right. So in the text, other relationships are the cost of mailing a package and its weight, minimum braking distance of car, perimeter of a rectangle, if the function has the length and the width, test scores someone makes, and the amount of hours they spent studying. These are all things that just two numbers, two values that are related. So when we have our ordered pair, x contains the set of x values is called the domain, and the set of y values is called the range. X and y and z, it turns out in math, and it's not a rule, it's just something that we do. We don't, when we're looking for variables, we typically go toward the end of the alphabet. So that's where you'll see W, X, Y, Z. We're not there yet. Not there yet, Andrew. But so toward the end of the alphabet is where your variables are going to come from. So you're used to seeing W, X, or X, Y, and Z as variables. Your constant terms, the numbers that don't change, A, B, and C, they all come from the front or the first 3 or 4 letters of the alphabet. And then in the middle, F, G, and H, it's not really the middle, but you get my idea. That's where our function names come from. So it's not a rule, it's just something that I think we've just done it so long, it's just an unwritten rule. But yeah, letters toward the end tend to be variables, toward the beginning tend to be constants, and then in the middle tend to be function names. All right, so here's an example of a relation, and we're asked to write the set of ordered pairs that defines the relation given in this table. All right, so I'm giving you, or I'm asking you to give me a set. I can list these things. We've run into 2 types of sets. We run into sets in interval notation where I'm talking about all the numbers between 2 values. And then you've seen the sets where they're not infinite, they're listable. They're things you can write down in a reasonable amount of time. So the ordered pairs that make up this relation are 8, 92, right? Because 8 hours of study gives you a 92, or that was the result of this experiment. 3 hours, so I studied 3 hours and got a 58. Someone studied 11 hours and got a 98. Someone studied 5 hours and got a 72. And then someone studied 8 hours and got an 86. Right. Now, if you're thinking, hey, that's not a function, you're right. I have 2 x values that are pointing to, I have the same x value pointing to 2 y values, but we're not there yet. So hold on to that. You're out in front of the game here. So for the domain is just all the x values. So that is what? Well, I've got 8, 3, 11, 5, and I have 8 again, okay? For domain and range, the sets do not repeat values. So notice I don't write 8 again. It's in there. I don't need to write it twice. The range, these are all your y values, so there's that y as an element of. And the values here are 92, 58, 98, 72, and 86, right? The domain is made up of all the x values in my table or all the x values in my relation. The range is made up of all the y values in my relation. If you want to write these in order, that's fine. It's not required in this one. Just pay attention to the directions because sometimes it's going to say write the set, list them in numerical order. All right? So that is domain and range. That's all it is. Domain, all possible x values. The range, all possible y values. Now, for this study, I say all possible. What I do not mean that the domain contains every single number ever, all the numbers that could correspond to the hours of study. The domain consists of all the possible x values for this relation. This relation only has 5 data points. So the domain here, the complete domain is 3, 8, or 8, 3, 11, and 5. The complete range is 92, 58, 98, 72, and 86. But I'm over analyzing that for a second. Okay. And then what I said here is that elements, and this goes for both, and the domain and range never repeat in set notation. And what I mean by that is the domain will never carry the same number twice. The range will never carry the same number twice. All right. So that's a relation. I've got something going on here. There's some kind of relation between the hours of study and the test score. Notice in your mind, you think, oh, there's definitely a relationship between those things. Yes, there is. What is that relationship? I don't know. All right, but that's beyond that scope of that question. That question just said, what is the set that makes up the relation? What's the domain? What's the range? Now, what is a function? A function is a special type of relation where for each value of x in the domain, there is exactly one value of y in the range. All right? So that means if I plug in 0 for x, the value I get for y should be unique. I shouldn't be able to plug in 0 and get 3 in one case, and then plug in 0 and get out 7 in another case. Whatever I plug in for x, it has one and only one value of y that it corresponds to. All right, so let's take a look at these 2 examples and determine, are these functions or are they not? So if I keep the same idea from the last, I've got a domain, I got a range, and this is A. So the domain, you're exactly right. The domains are going to consist of 3, 2, -4, -1, and there's 3 again. Okay, so we got a problem. The range consists of 1, 5, 2, 0, and -4. And the relation is 3 points to 1. In other words, I take 3, I plug it into my relation, and I get out 1. How does that work? I have no idea. I don't need to know anything other than I plug in 3, I get out 1. Next one, I plug in 2, I get out 5. Plug in -4, I get out 2. Plug in -1, I get 0. And then the last one, I plug in 3, and I get -4. And this is where it breaks the rules. right? The rules for the function are for each value of x, there's exactly one y value. Okay, this is not a function. It's still a relation. Okay, it's just not one that's really going to give us anything, or it's not one that meets the definition of a function. Now, for letter B, my domain and range consists of the domain is, and I'm down here in this example too. I'm just pulling all the x values out: -1, 2, 3, -4, and then the range is 4, 3, 4, and 5. But I told you we don't repeat values, so 4 is in there already, so I don't write it again. So the range only consists of 3, 4, and 5. What's the relation? -1 points to 4, 2 points to 3, 3 also points to 4, and -4 points to 5. This is a function because every x value has one y value that it points to, right? Every one of the values in the domain only has one arrow leaving it. The -1 goes to one place, the 2 goes to one place, the 3 goes to one place, the -4 goes to one place. It can be confusing, but when you consider the relations in this form, when you're just kind of looking at them as just arrows across, if any x value has 2 arrows leaving it, it's not a function. If all the x values only have one arrow corresponding to it, it is a function. Technically, all of these could point to one number in the range, and it's still a function because it's all about. I could have -1 point to 4. I could have 2 point to 4. I could have 3 point to 4 and -4 point to 4, and I'm still a function because each x has only one y that it's pointing to. All right. So the range can have multiple arrows coming toward it, but the domain can only have one arrow leaving it. And that's the difference, or that's the definition of I have a relation, and then that relation has a special feature, and that feature is that for every x value, I point to only one y, and now that relation is known as a function. Okay. And then there's just a little tip as a reminder of what we're talking about here. It's all about the arrows leaving the x's. If there's multiples of those, that's a problem. If the values in the range, or if something's being pointed to a bunch in the range, it doesn't matter as long as each arrow leaves one and only one x. All right. Now, when I have a relation that's not a function, what happens? Well, take a look at the example we have. I went from 3 to 1 and 3 to -4, right? So here we're over here in our example, 3 to 3, 1, 3, -4. What is that graph like? Well, if I go graph those 2 points, here's 3, 1, here's 3, -4. If I have one x value in the domain that's pointing to multiple y values, when I graph it, those 2 points are going to be on a vertical line, okay? Because they both have the same x value. And this is what leads us to the vertical line test. All right, so we've got this conceptual idea. We've seen it with ordered pairs. Now we're going to take it over to a graph, and instead of just having points in my relation, now I'm going to have an entire curve, or an entire stick with curve, an entire curve in there. Okay. If at any point I can draw a vertical line and hit 2 points of the graph of my function, of the curve of my function, the curve that I've plotted, I don't have a function. Vertical line test is something people tend to remember, so this is probably not that alien to you. So here are 3 examples. The functions are, the relations are in blue. The little arrows are added just to show you. Here's the idea. If I can draw a vertical line anywhere and hit the curve more than once, I do not have a function. for part A, we've got arrows all over the place, okay, but I'm never hitting the curve more than one time. So part A, that's a function. Part B, it only has to happen once and only in one place, but I have a vertical line and I have hit here and here. What does that look like when I do the ordered pairs? This point is 2, 2, and this point is 2, negative 2. The x value 2 points to 2 and negative 2, and that's what causes the problems, and not a function. And then the last one, okay, obviously nothing over here to the right is a problem because this is called a piecewise function. Everything down to the left is fine because the function never crosses itself. But whenever you see these piecewise functions and you see these circles on the endpoints, this is the place where if you're going to fail the vertical line test, it's going to be on one of these endpoints. In this case, if I draw a vertical line on the line x equals 1, I don't hit the function here, but I do hit it here. That's only one time. So this is a function. Okay, it's all about that vertical line test. Okay, so those are the 3 examples the book gives. Let's look at the 3 examples that it wants us to do on our own. All right, so there is part A, part B, and part C. And again, it's just, can I draw a line and hit the curve twice? Yep, I've done it right there. Everywhere on that one, right? There's no place at all. If as long as I hit the curve, I'm always going to hit the curve twice, right? So A is a no. B, yep, is a yes, because you can draw as many vertical lines as you want. The curve never crosses over on itself. So A, no. B, yes. And then C. I told you this one, so this is another piecewise. I don't have to worry about anything for x greater than negative 2. Yeah, I don't have to worry about anything for x less than negative 2. But I do have to worry about the place where the piecewise overlap, and we do have a problem there. Right? We have a problem right there. And I cannot draw directly on top of it. Well, that's unfortunate. Well, it won't jump on top, but let's see. Has never been a problem before, but here's the idea. Let's pretend like I can draw straight lines. And there's a straight line, straight vertical line. And what have I done? I've hit my function twice. So this is a no. All right. So vertical line test. That's all we're after here. All right. Now, the tip down here at the bottom just drives home the point whenever I have that piecewise. Why is this a function and this not a function? It's because when that piecewise, the value of x where one ends and the other begins, one's an open circle, one's a closed circle. On this one, they don't end and begin. This one ends at negative 2. This one starts at negative 2. So that means if I were to write these as ordered pairs, I would have negative 2, 2, and negative 2, 4 in my relation. 1x value to 2y values. All right. So that's the idea. So we've seen a relation in ordered pairs. We've seen some graphs, and we've determined if they're functions. Now let's talk about function notation. So f of x, this f parenthesis x is read as f of x. Okay? It is not f times x, even though that's exactly what it looks like, right? If I tell you 5 times x is 5x, right? That's what it would mean if it were written. This is a special case where there's no operator between the f and the x, but we are dealing with functions, so we know that whenever I encounter this, I'm looking at a function. I'm not looking at f times x. Okay, Some people say f of x is just the Grey Poupon of math, where it's the fancy way to write y. So y equals x plus 3 is a function. It's a function because, so this is a linear equation. It's a line. Straight lines, as long as they're not vertical, will never fail the vertical line test. So there is y is equal to x plus 3. Function notation, all it's going to do is swap out that y for f of x. Okay, why do I want to do that? Well, the reason I want to do that, there's a couple of reasons I want to do that. The first one, now I have a name, right? This relation between y and x has a name, and the name is f. Okay? The other reason we like to see this is if I asked you to plug in what is y when x is 2, then you would need to write, we're going to let x be 2, and then we're going to say y is equal to 2 plus 3, which means y is 5, which means, so I've got y is 5. If I want to ask you that same question in function notation, all I do is replace whatever value of x I'm interested in, replace x with that value. So instead of having to write find y when x is 2, all I have to do is write f at 2. And that immediately means on the right-hand side of the equation, everywhere there's an x, you swap it out for a 2. So I get to the end, and look at what I have. I have f at 2 is equal to 5. That corresponds to an ordered pair 2, 5. I didn't have to go back and remember what I plugged in for x. I didn't have to go back and check because I know what I plugged in because it's sitting right there inside the parentheses. On this problem, if I don't use that function notation, then I have to come back to the beginning and remember, oh yeah, I plugged in 2 for x and I got out 5 for y. I know it doesn't seem like that much of a hassle, but it's going to come in handy later. Also, by naming it a function, you're indicating to the reader that what they're looking at is a function, so that automatically gives them ideas on do I have multiple, a single x's that point to multiple y's? And the answer is no. So if this is the case, I've got a little bit more, I got a trinomial, got a quadratic here. Y is equal to x squared plus 3x minus 4. I'm going to swap out y for f of x. And I want you to find the following values. Find, and so I told you this is read as f of x. You'll hear me say this as f at 5, not f of 5. So this reads, whenever it's a number in there, it's going to read as f of 5. All right. This reads as f of x, or f, and this would read at f of 5 or f at 5. F at 5. All right. So f at 5. Okay. Well, f at 5. F at x is x squared plus 3x minus 4. So f at 5, what's that going to be? Well, everywhere there's an x, plug in a 5. So that's x squared plus 3 times x minus 4. Okay, here's the original. Let me get rid of this red here. Don't need that in the way. So take a look. What did I do? F at 5. I just took f of x and I swapped out everywhere there's an x. Now there's a 5. I always use parentheses to, in this case, they're not necessary on the first one, but they're very helpful. They help you avoid making mistakes. So anytime I swap out x for a variable or a variable for a constant, I always write it in parentheses. And now I have 5 squared, which is 25. I have 3 times 5, which is 15, minus 4. So that's 25 plus 15 minus 4. 25 plus 15 is 40. 40 minus 4 is 36. And then there's my answer. And right there in just a minimal amount of notation, you can show me that you understand what you're doing. Because now you've told me what's f at 5. F at 5 is 36. When I plug in 5 for x, I get out 36. All right. Let's finish the number ones, and then we'll deal with the ones that have letters in them. So f at 0, even when it's 0, it's never a bad idea to use a parentheses. If you don't use a parentheses here, this would look like 30, right? And you're exactly right, Andrew. F at 0 means every term that has an x in it is going to go to 0 because I'm multiplying it by 0. So this is going to be 0 squared, which is 0, plus 3 times 0, which is 0, minus 4. 0 plus 0 minus 4 is negative 4. So f at 0 is negative 4. And like I said, I'm going to cheat and jump down here to the f at negative 1, and then I'm going to come back and deal with the other three. So f at negative 1, well, that's x squared, which is negative 1 squared, plus 3 times negative 1 minus 4. Negative 1 squared is 1. 3 times negative 1 is negative 3, so that becomes minus 3 minus 4. 1 minus 3 minus 4. 1 minus 3 is negative 2. Negative 2 minus 4 more is negative 6. All right, so in all three cases, if I give you a value for x, or whatever the variable is that you're looking at, and I ask plug it in to the function, tell me what you get, this is how you do it. Fairly straightforward. Notice all three of these, I've plugged in numbers for x, and I've gotten a number for f at that value. When I come up here to the top and you see f at negative x, what does that mean? You haven't seen that before. Don't overthink it, okay? When we create notation in math, we try to keep it consistent all the way through. That is f at negative x. So that means everywhere there's an x, swap it out for a negative x. Right? So negative x times negative x is positive x squared. 3 times negative x is negative 3x. And then that's all I can do. Okay. Most students tell me the hardest thing in math is knowing when you're done with a problem. In that one, there's no more math to be done. All the terms are unlike. There's an x squared term, there's an x term, there's a constant term. None of them can be combined. I'm not worried about factoring here. It would factor, but I don't need to factor it. There's no reason to. Okay. Now, here's the one that can cause some issues. I have negative f of x. Remember, f of x just means y, right? Well, or f of x is y. Well, what is f of x? F of x is the original, it's the original function, right? So f of x is x squared plus 3x minus 4. Well, negative f of x means negative, and then I just plug in x squared plus 3x minus 4. It's an odd one because this is the only time where I'm not, what's not changing is what's in the parentheses. What's changing is on the outside. So f of x is x squared plus 3x minus 4. Everybody cool with that idea? That was given at the beginning. So negative f of x, all I did is substitute x squared plus 3x minus 4 in for f of x, right? This is like someone calling you Nick and your full name is Nicholas. It's the same thing, okay? And then what do I get? Well, that's a that distributes to negative x squared minus 3x plus 4, and that's it. That's all I can do here. I don't think there's any more simplification to be done. Like I said, you can factor this if you want. Yeah, you can factor those, but that's not the point in this yet. That's not where we're after. We're just trying to get comfortable with function notation. All right, and then for the last one here, f of x plus h, if you understand this, if you can wrap your head around this part, you're going to be in great shape, because what's happened is in place of x, I now have, it's a binomial in there, right? I got two terms. So everywhere there's an x, I swap it out for x plus h. Remember the original function, okay? And if we need to write it, let's look at it. The original function is f of x is x squared plus 3x minus 4. So everywhere there's an x, I swap it out for an x plus h. So that's x plus h squared plus 3 times x plus h minus 4. You're already on it here. Don't forget, x plus h squared, do not distribute that power to the x and the h and stop. That means x plus h times x plus h. For the middle term, I need to distribute that 3. So I've got 3x plus 3h minus 4. And then I'm going to come back over here and deal with the multiplication I have at the beginning. This is two binomials, so we're doing FOIL. First times the first is x squared plus outer xh, inner xh, last h squared. All the terms I had, 3x plus 3h minus 4. And then anytime you multiply a binomial, the two middle terms tend to be like, so you can combine like terms here and get 2xh plus h squared plus 3x plus 3h minus 4. It's hard to believe that there's nothing that will there's nothing in here that's like, but there's not. There's nothing left to do. Right? This is an x squared. This has xh. This is an h squared. This has just x. This has just h. None of them are alike, so I cannot combine anything else. Again, the tough part of this one is going to be figure out when you're done. All right? So let's do another one, just because I think the practice is good. And we're going to come over here to g of x. So g of x is 8x over x squared minus 9. I'm not going to, I'm not going to factor this. That is the difference of perfect squares. I'm not going to break this up into x plus 3 and x minus 3. And the reason is, what I'm being asked to do is not reduce. It's not like there's an x plus 3 or x minus 3 or the possibility of an x plus 3 and an x minus 3 up here. So I'm not going to take the time to do that. We'll get a feel for the problem and figure out what we want to do. So g at -1. That x gets replaced with the -1. The x in the denominator gets replaced with a -1. 8 times -1, -8. -1 squared is 1. 1 minus 9 is -8. -8 divided by -8 is 1. So I have found g at -1 to be 1. If I want to plot that on a graph, can somebody tell me the ordered pair that corresponds to this answer? What is the x value and what is the y value that I'm interested in here? Right, and so -1, 1, but remember that it's an ordered pair, so it has to be inside parentheses. So it would look like that. So there's the function notation. There's the point that I would go to, and you can see all of that information by just using the function notation, right? It's all there in the last step where you reveal your answer. Let's go over to the top right, g at 0. G at 0 is 8 times 0 over 0 squared minus 9. 8 times 0 is 0. 0 squared is 0. 0 minus 9 is -9. When 0 is in the numerator, as long as 0 is also in the denominator, then this always just comes out to 0. Because think about what a fraction is. A fraction is, this is how many places, how many pieces a whole is cut into, and this is how many we're interested in. right? 0/9 means it's like taking a pizza, cutting it into 9 pieces, and then saying I'm not going to eat any of them. Okay, it doesn't do, it's just nothing. So G at 0 equals 0. Okay. All right. How about G at -x? G at -x means take all the x's and swap them for negative x's. Now take a look at what happens with my signs. 8 times x is -8x. So in this one, that negative impacted the numerator, right? In the denominator, though, I've got -x squared. So -x squared just becomes x squared. So take a look at that. What's happened here is that my denominator is not impacted by the negative sign on the inside of the x because the term, the x term is raised to an even power, right? The denominator comes out exactly the same as it was. The numerator has switched signs. So -8x over x squared minus 9. You can also put the negative out front. Both of those are acceptable. It just depends on which one makes more sense to you. -8x over x squared minus 9. All right. So how about G at 5? G at 5, that's 8 times 5 over 5 squared minus 9. 8 times 5 is 40. 5 squared is 25. 25 minus 9 is 16. And then this reduces to what? These both have a factor of 4. So that's going to give me 10 over 4, right? Divide top bottom by 4. And then they're both still even, so this is going to end up as 5/2. Nothing left in common. So G of 5 is 5/2. All right, G at 3. G at 3 is, if I remember correctly, it's just 8x over x squared plus 9. So that's 8 times 3 over 3 squared minus 9. I said plus, and I should have said minus. 8 times 3 is 24. 3 squared is 9. 9 minus 9 is 0. And that is a problem. And the reason is we actually don't know what dividing by 0 would do. I think dividing by 0 is what causes black holes, okay? Because the question is, how many times does nothing go into 24? It's a nonsensical question. So whenever we run into this, whenever we encounter this, we say G at 3 is undefined. Okay. So that just means when you plug in 3, the function doesn't, what it means is the function, it causes division by 0. So we don't know what that means. The reason we don't know is if we pretended, and let's just knock out this one, and then I can give you a little side rant here. This is G at alpha, okay? G at alpha is 8 times alpha over alpha squared minus 9. 8 times alpha is alpha. Alpha squared is alpha squared minus 9. All that did is just replace all the x's. It didn't really do anything else. All right. So there are our problems. Now, on the 0 stuff over here, just as an aside, let's pretend like 5 divided by 0 gives us 0, okay? And the way we would write that is suppose 5 divided by 0 is 0. Does everyone agree that if 6 divided by 2 is 3, then 2 times 3 is 6? Do those follow from each other? One follows from the other. This is an if and only if. If 3 divided by 2, 6 divided by 2 is 3, 3 times 2 is also 6. That's pretty concrete, right? If we apply those, so we suppose 5 divided by 0 equals 0. Well, if that's true, then 0 times 0 equals 5, and that's impossible. Okay? If you assume dividing by 0 leaves you something else, something other than 0, you're still going to end up with a problem that says 0 times some number is something that's not 0. So this is why division by 0 is undefined. All right. Questions on that? All right. And let's deal with intercepts. Okay. Intercepts, I'm going to have two of them. I'm going to have an x-intercept and a y-intercept. The x-intercept is literally the point where my graph or my line or my function crosses the x-axis. I have a y-intercept, and the y-intercept is literally where the function crosses the y-axis. How do I find these things? On a graph, it's super easy. In a function, if I don't have a graph with it, it's not that easy. So let's assume I have some function f of x. All the x-intercepts, I'm going to find them by solving the equation f of x equals 0. I'm going to take the function, set it equal to 0, and solve for x. We've been doing that for a while now. The y-intercept is going to be given by f at 0. Well, isn't this nice? Look at how short they put this. The y-intercept is given at f equals 0, or f of x, let me say it right, f at 0. So this tells me what? X is 0, and then solve. Right? Let x be 0 and solve. All of said in just that short function notation. All right, so let's deal with this example and see if we can find the intercepts. Now notice the plural, x-intercepts are plural here. You can have multiples of those. Y-intercept is not plural. That's because you can only have one. If you have multiple y-intercepts, you don't have a function. All right, so let's come out here to the side and deal with our problem. Find the x and y intercepts of the function f of x is equal to x squared minus 4. All right, so let's go after the y-intercept first because I think it's easier. So in the y-intercept, when is it going to occur? It's going to occur when I let x equal 0, right? So x is 0 means take f, take your function, plug 0 in for x, and solve. 0 squared is 0. 0 minus 4 is negative 4. All right. So, and then here's the thing about x and y intercepts. X and y intercepts are points. Okay. So the y-intercept is the point 0, negative 4. Okay. Now the text or the homework online may only ask you to write negative 4, but I want you to know mathematically the y-intercept is a point. It's not just a single number. Okay? When x is 0, y is negative 4. All right, so that's x-intercepts. How about, or excuse me, that's y-intercepts. How about x-intercepts? Well, x-intercepts, what do? I let y be 0. Okay, well, change that to my fancy notation. So that means I'm letting f of x be 0. If my original problem is x squared minus 4, and I say let f of x be 0, this left side is f of x. So f of x is 0. Solve for x. What do I have? I have the difference of perfect squares on the right. So that becomes x plus 2 times x minus, I don't know why I put a 1 there, x minus 2. My favorite principle in the whole world. By the zero product principle, I have two things that multiply to 0. So either x plus 2 is 0 or x minus 2 is 0. If x plus 2 is 0, then subtract 2 from both sides, x is negative 2. X minus 2 is 0, add 2 to both sides, x is 2. Now, 2 and negative 2 are not the intercepts. The intercepts are points, right? So these correspond to points. Okay? One of them has a value of x is negative 2. One of them has a value of 2. What's the y value for both of these? Something and 2. Something. What did I let y be to start with? What was my very first step? I let y be 0, exactly. So x-intercepts are 2, 0, and negative 2, 0. Great. So again, you can have multiple x-intercepts, but you can only have one y-intercept. Because if you have multiple y-intercepts, you're not a function anymore. All right. So that's finding intercepts. Let's go hunt some domains real quick. All right. So the guideline at the top is going to inform us on how to do some work on the next page. So I want you to just take a look at the example of 8. So example 8 here tells us, here are the graphs. Here are 3 graphs. Tell me the domain and the range of each. Okay. Well, that one's easy because these are all points, right? We just got to figure out what are the points. This is negative 3, negative 4, and we can go through that. We don't need to write them all down. All I'm asked for is the domain and the range. So the domain, x is an element of, and I'm going to list all my x values. And they are what? Well, I have an x, this point, and at this point, x is negative 3. At this point, x is negative 1. At the point in the middle, 0, 1, x is 0. Up here, x is 2. And then the last point on the right, x is 4. Okay. Right, if I were listing the ordered pairs, I would. But since it's just the domain and the range, they didn't ask for the relation or the function itself. They just asked for the domain and the range. And the reason that I'm using brackets here, the curly braces instead of brackets and parentheses, is because I can list all these values. There's just single values here, right? So for y, what I did for the domain right there is I pretty much just kind of looked at it vertical. I just took as the idea of a vertical line, and I just moved from left to right, and whenever I hit a point, I added it. So I hit that point, that's x is negative 3. I hit that point, x negative 1. Hit that point, x is 0. Hit that one, x is 2. Hit that one, x is 4. When I want the y values, I just flip this to a horizontal line. I'm going to start at the bottom. The first y value I encounter is negative 4. The next one is 1. And then after that, keep moving up. And then I encounter 3, and then I encounter 4. Okay. Now, I encounter 4 twice. but I don't write it twice because I never have repeated values in the domain. I never have repeated values in the range. That does not mean that the same number can't be in both the domain and the range. That means if it's in the domain once, it's not going to be written again. If it's in the range once, it's not going to be written again. So there are the domains and the ranges. All right. For part B, so now I cannot list all the X values and Y values in the domain and range because I have a line or I have a graph, right? And so instead of being able to write these out and list all the values, I'm going to have to use interval notation to write it. So when I'm looking for all the X values, okay, if I think of this as just like I did before, if I want to find my domain, I pretty much take a vertical line and I work my way over until I hit the curve, and I start at -3, but I don't actually touch it, right? So I start at -3. I continue, if I keep moving my line, I continue hitting the graph forever and ever and ever. And then that arrow up here tells me two things. First, it tells me that this behavior goes on forever. And second, it tells me the function never does anything, never changes direction again. So because there's an arrow on the end, that means this function doesn't suddenly drop again and rise again. If it moved up or down again and did something other than this behavior, we'd have to graph that. And when the function finally reaches a point where it continues the same behavior forever, that's when we put the arrow on the end. So for X values, I start at -3 and I go on forever, so that's off to positive infinity. Infinities never get brackets, and then is the -3 included? If I plug in -3, do I hit this function? No, I don't. There's an open circle there. So that means parenthesis for the domain. About the range. Same game, right? So for the range, I get my line. I'm going to start at the bottom and work my way up. The first place I get close to touching the function is -2. I don't actually touch it there, so that does get a parenthesis. And then I continue that all the way up to the arrow, which goes on. So this means this behavior continues forever. So that means this function's rising forever. And forever in math is infinity. All right. Questions there? All right, so let's look at the last one. I'm going to grab my line and start from left to right. And as I move from left to right, notice that in part A and B, I'll keep moving and then I'll hit a point. I'll either hit an open circle or a closed circle. And this one I don't. The first time my vertical line touches this curve is when the function has an arrow on the end of it. And remember, we talked about if the function has an arrow on the end, that behavior continues forever. So this function, while this is just part of the graph, this goes on forever, okay? Like forever, ever. Forever, ever, ever. All right? So that means if this behavior continues forever, and I know it can't go back up, I know it can't curve back to the right, because if it did, it's not a function. If this behavior continues forever, then there is no limit on how small x can be, right? I have no limit on how small it can be. So as I move from left to right, x is always defined. So that means my domain starts out at -infinity, and then as I move to the right with my line, I keep hitting, and then I get that arrow, and the arrow is pointing down, so I'm dropping as I go. So that means I'm dropping as I go, but I'm moving to the right at the same time. So there's no limit on how large it can be. So the domain here is all real numbers. The range, on the other hand, is not. Now, when I move up from the bottom, I hit those arrows first, so that means the function continues going down forever. So here's the tricky part about the range, though. Your lowest value is at the bottom of the graph. So I'm starting out at negative infinity, and then I work my way up until I stop hitting the graph. Where do I stop hitting the graph? Just above 4. Right? Just above 4 is where I stop hitting it. So the range ends at 4. This is not an open circle at the top. And since there's not an open circle, it's understood that 4 is part of the range. So it gets a bracket, or a brace, excuse me. Okay? But the range stops at 4. Why does it stop at 4? Because there's no value of x you can plug in and get 5 or 6 or 7 or anything greater than 4. 4 is as high as it goes. All right. Questions? No? These are going to take time and practice, so be prepared to do them. So be prepared to take the time to do the practice. All right, so I'm going to skip the guidelines here, and I just want to see if we can tackle these last 2 pages, and then I will have some guidelines to finding domains algebraically in the beginning of the next class, if we run out of time, which I think we will. So here's our graph, and we're asked to do pretty much everything we've done up to this point in this graph, all right? So I'll make it a little larger. It makes printing look a little weird when I do that. But there's the function. Okay, I know it's a function because it passes the vertical line test. And I'm asked to determine a few things. So find f at 2. F at 2, what does that mean? That means x is 2. X equals 2 is a horizontal line, right? Excuse me. X equals 2 is a vertical line, like I said, of course. So I take my vertical line and I go over until that vertical line is the line x equals 2. Where's x equal 2? Right there. All right, and again, I can't get these to be dead straight with the graph. But that's the idea. Right? So when x is 2, what is the function? Up here. Where does this top out at, or where does this hit? It hits when y is 5. So f at 2 is 5. Okay? How about f at negative 5? When f is negative 5, okay, I go over f at negative 5. Uh-oh, I got an open circle there, right? So f at negative 5 is undefined. Or let me be a little picky here and say is not defined. Just so we don't confuse these two. Division by 0 did not occur. The function just ended. Okay? So since it ended, plug in negative 5, it doesn't do anything. It's when you plug in and you cause division by 0, that's when we want to go with undefined. In this case, I'm saying not defined because the graph just doesn't go over there. Negative 5 is not part of the domain, so it's just not defined. Part C says find all the values for f of x is 0. Okay. F of x equals 0. F of x is just y. Right? Y equals 0 is a horizontal line. And it's not just any horizontal line, it's the x-axis, right? every point on the x-axis has a y value of 0. So all I gotta do is go through here and look and see where does, what are the values of x where I hit that axis. And they are -4 and +4. All right, so there they are. -4 and +4. They did not. Now, why didn't I put this in an ordered pair? Because the problem did not say, or it didn't say give me the intercept. It just said find all the x where f of x equals 0. Those are the x's where that's true. Part D says when f of x is equal to 3, find x. When f of x is 3, that's a horizontal line. Ooh, we got something interesting going on here. When f of x is 3, I don't just hit this at some points. I actually hit it on this entire interval right here. And I hit again right here. How am I going to do that? How am I going to write that? Well, this interval, anytime I'm talking about an interval for my looking for values of x, this is part of my domain. And it starts at -3 and it goes until 1. If you plug in any value of x between -3 and 1, you get out 3, right? Does everybody agree to that? If I plug in anything, if I plug in -2, I get out 3. If I plug in -1, I get out 3. If I plug in -2.5, I get out 3. It always happens. It keeps happening over and over again. So I need to write this interval that starts at -3 and goes until 1. The endpoints are not open circles, so they are included. So that gets all of those, but I have something else, right? I have another part. This function also crosses the line y equals 3 right here. Now, the way I see that is that looks like, what close do I need to get? At 3, it looks like I'm right here. I'm just to the left of x is 3, so I'm going to call that -2.9. That's the point, and it's not negative. It's positive. I really wish it was right on that edge, but it's not. So when y is 3, I hit right here, so that's 2.9, something like that. So that means 2.9 is also part of my answer. So I need to write just a single number, 2.9, and put it in the solution set as well. How do I write single values or things that I can list? I put them in curly brackets, curly braces. And then these are two sets. I need to put them together, and I do that with the union. All right. Now, part E and part F says find the x-intercepts. Okay. There's no math to be done because the x-intercepts are just go right up here to the line. Where do I cross? -4 and +4. So -4, 0 is an intercept. 4, 0 is an intercept. For the y-intercept, we know there's only going to be one of those, if there are any. Where do I cross the y-intercept? Cross it right there. And what is my x? My y value is 3. My x value is 0. All right. X-intercepts are always going to have this form. Some number, comma, 0. Y-intercepts are always going to have this form, 0, comma, some number. For the x-intercepts, remember, I let y be 0, I solve for x, so my non-zero numbers or in the x place. And then for the y-intercept, I let x be 0 and I solve for y. All right. All right, well, let's call it there for the day. I've got 2 more pages that I'm going to add to this, and I'll post that with the last problem done, just like we're doing right now. And that lecture will go on to our YouTube list. So are there any questions?